The forecast was incorrect, not by a small amount, nor within a typical margin of error. The heat dome that all major prediction systems indicated would be weakening is instead intensifying. It has reorganized, seemingly absorbing its own projected demise only to emerge stronger. By Wednesday, it is expected to settle over Colorado, posing a threat to a temperature record that has stood through 2 world wars, the space race, and every summer since 1915. At the same time, this very system is creating the fire weather conditions that fueled the second largest wildfire in American history. It is a single ridge, producing 2 catastrophic outcomes simultaneously. And based on seasonal patterns, this shouldn't even be the most hazardous part of the year. If a heat dome that defied its own collapse to challenge a century-old record while also priming the most dangerous fire conditions in modern American history has captured your attention, we invite you to continue this journey with us on Calm Space. The ridge is still advancing, the window for fire weather remains open, and a gap is widening between official forecasts and what the atmosphere is actually doing. We believe it is essential to track that divergence in real time. Something is amiss in the atmosphere, and the professionals who monitor it daily are not concealing their concern. This isn't the dramatic, fleeting alarm designed for clicks, nor is it the vague hedging that meteorologists sometimes employ when faced with uncertainty. The worry emanating from National Weather Service offices across the nation is of a different nature, specific, technical, and quietly urgent. It is the kind of concern that prompts forecasters to choose their words with exceptional care. It is a situation where the language within official discussions begins to shift in ways that are only noticeable if you have read enough of them to recognize what normal sounds like. And at this moment, little of what they are writing sounds normal at all. To understand the gravity of the situation, we must start here. The May 2026 heat dome, which has already been scorching the American southwest and southeast for nearly 2 weeks, was expected to be dissipating by now. This is not a matter of opinion. It was the consensus of the atmospheric models and the prevailing setup. A heat dome typically builds, reaches a peak, and then the ridge of high pressure that contains it gradually weakens. The pattern breaks down and the heat disperses. This is the established life cycle. This is how these systems are supposed to behave. Except this one did not follow the script. Rather than collapsing, the western ridge of this heat dome did something that truly startled its observers. It intensified and expanded. Then, it began to move. It was not dissolving into the background atmospheric noise as a weakening pressure system should, but was instead undertaking a physical migration inland. It is like a slow-moving wall of high pressure, rolling east across the Rocky Mountains and extending its influence over the center of the country. By Wednesday of this week, that ridge is projected to be positioned directly over Colorado, sitting atop the Front Range and the plains with enough strength to push Denver into a temperature range of 89 to 91 degrees Fahrenheit. This range overlaps with a daily record that has remained unbroken since 1915. Let the significance of that year, 1915, settle in for a moment. This is not a record from the 1980s, when modern climate change was already a known factor. It is not from the 1950s, or even the Dust Bowl era of the 1930s, though we will return to what that parallel can and cannot teach us. The year 1915 predates World War I. It predates commercial radio. It is from a time before the Model T Ford was widely accessible to the average American. A person standing outside in Denver on the day that record was set likely wore a hat and a waistcoat and had probably only read about airplanes in newspaper headlines. No one alive today was there to witness it. That single temperature record has survived 11 decades of American summers through heat waves, droughts, and every form of atmospheric extreme the nation has since produced. And now, it lies directly in the path of a ridge that, according to every running forecast model, simply refuses to die. That fact alone would constitute a remarkable meteorological story, a century-old temperature record threatened by a weather system that has outlived its own predicted end. But this is where the narrative broadens beyond a single number on a thermometer. And it is this larger picture that is genuinely fueling the concern within NWS forecast offices. The very same ridge that is menacing Denver's historic record is simultaneously doing something else entirely, something that has little to do with temperature readings in cities and everything to do with open grasslands, dry winds, and the physics of combustion. The National Weather Service office in Bismarck, North Dakota, has issued warnings for several days of critical fire weather conditions across the northern plains. Not a single afternoon of heightened risk, nor a brief window of concern, but several consecutive days of the precise atmospheric configuration that fire behavior analysts classify as the most dangerous possible combination of ingredients for the spread of large, uncontrollable wildfires. If you are familiar with fire history, that phrase, critical fire weather, across the northern plains, should send a chill down your spine. It describes the same configuration, the same winds, the same relative humidity, and the same dry fuel alignment that led to the Smokehouse Creek fire in 2024, the second largest wildfire in the history of the United States. It is the same setup that produced the Marshall Fire in 2021, the most destructive wildfire in Colorado's recorded history, a fire that burned in December in snow country, in a suburban area that no one believed was at serious risk, because the words fire and December did not historically belong in the same sentence in Colorado. It is the same atmospheric pattern behind the most severe single fire event in modern North Dakota history. What we are actually witnessing then is not just a heat wave. We are watching a single, unified atmospheric structure, this unrelenting ridge that refused to collapse, simultaneously generating record-breaking heat in urban Colorado, multi-day critical fire weather across the northern plains, and, as we will explore further, severe weather outbreaks along its eastern edge, where it collides with moisture from the Gulf. It is a multifaceted event that forecast models are flagging with increasing alarm, pushing the limits of our predictive understanding. A single atmospheric system can unleash a cascade of consequences, each one significant. This event, however, raises a question that cuts to the core of our understanding of weather, a question for which there is still no simple answer. What are we to make of a weather pattern that defies its own established life cycle? We are left to wonder how a high-pressure ridge, which all historical data and standard models predicted would weaken, instead intensified and began to march eastward. This was the second such event of this scale in 2026, occurring even before the formal Super El Nino had reached its peak, which was still about 6 months away. This timing forces us to consider what the next 18 months of weather across America could hold. If 500 year-class heat events are beginning to cluster before the primary climate driver is fully active, we may be facing a problem far larger than any one heat dome or fire season. It is possible we are witnessing a fundamental change in the behavior of the atmosphere over the continent. Even the forecasters, choosing their words with unusual care, seem to sense this shift. They know something profound is happening. The challenge is finding the language to describe it. To grasp the significance of a ridge that refuses to dissipate, we must first examine the system's initial state. The May 2026 heat dome originated as a formation known to meteorologists as an omega block. The name is a direct reference to its appearance on a weather map. When tracing the path of the upper-level winds, the jet stream forms a distinct shape that closely resembles the Greek letter omega. This structure consists of two separate ridges of high pressure, one positioned along the west coast and the other over the southeast. Between these two high-pressure zones, a trough of lower pressure dips down, creating the central feature that defines the omega shape. This visual detail is the key to its powerful nature. An omega block is one of the more formidable atmospheric patterns in the mid-latitudes. It is not a gentle or transient feature. Its power comes from its ability to lock weather systems into place for extended durations, as the dual ridges act as barriers, resisting the typical west-to-east flow that normally keeps weather moving. This blocking action prevents any single area from experiencing relief. As a result, when an omega block becomes established, heat can build under the western ridge, while a separate zone of heat intensifies under the eastern one. Meanwhile, the region beneath the central trough can be completely cut off, experiencing entirely different conditions. This is a pattern that inherently generates simultaneous extremes across vast areas, which is precisely what occurred during the first phase of this event, as it baked both the southwest and the southeast concurrently. But these powerful omega blocks are not permanent. They follow a predictable life cycle. The expected conclusion for this one seemed logical on paper. As the daily cycle of peak solar heating began to wane, the eastern ridge situated over the southeast was forecast to weaken. This is the normal progression and was supposed to initiate a cascade of events. With the eastern ridge losing strength, the central trough would fill in, causing the entire blocking pattern to lose its structural integrity. The jet stream would then resume a more typical, progressive flow, and the western ridge would subsequently dissipate. The pattern would be over, the heat event would end, and the models would move on. However, something the models were not fully anticipating became evident. The western ridge simply did not adhere to this expected sequence. As forecast discussions from the Weather Prediction Center revealed over the subsequent days, the western ridge did the exact opposite of what was predicted. Instead of weakening in tandem with its eastern counterpart, it began what the WPC described as a building and warming phase. It was not collapsing, but building. It was not cooling, but warming. And it was not retreating, but actively spreading into the central United States. This unexpected reversal marks the event's structural flip, a fundamental change in the system's behavior. What had started as a two-ridge omega block was now reorganizing itself into a completely different entity. The system transformed into a single, dominant ridge centered over the western United States. This new formation was not merely holding its position, it was actively expanding its influence eastward. It began to push across the Rocky Mountains, a formidable barrier to atmospheric circulation in its own right, and establish its presence over the high plains, with its sights set on the broader, central part of the country. This transformation raises the question of what this new, more unified structure is capable of. To understand why this transition is so critical, it helps to look at the physics of how these ridges move. Atmospheric ridges are not fixed in place like mountains. They are dynamic regions of organized high pressure, maintained by converging air high in the atmosphere and sinking air below. Their central axis of intensity can shift as the forces sustaining them evolve. In this case, as the western ridge absorbed the energy that was once divided between two separate blocking centers, it effectively consolidated the entire pattern. A single, consolidated ridge possesses very different propagation dynamics than a two-ridge blocking event. It is inherently more mobile, able to translate, or physically migrate, in a way the more rigidly locked omega configuration was designed to resist. So, what we are observing is not simply a heat dome relocating, it is a complete structural reorganization of the atmospheric pattern over the continent. The resulting single, dominant ridge is now marching eastward, and the true danger lies in what it carries with it. The ridge is not just moving, it is advancing with its full forcing capability intact. This means that every region it passes over will experience something close to the heat dome's full intensity. Not a diluted or weakened remnant. The system is exporting its extreme conditions to new areas without losing its power. Adding weight to this forecast, is the fact that two major ensemble modeling systems, the American GEFs and the European ESONs, are in high agreement about this eastward trajectory. When ensemble models, which work by running numerous slightly different simulations of the atmosphere to see where they converge, show strong agreement on a rare or unusual pattern, it is a signal that demands attention. This consensus among the models provides a high degree of confidence in a forecast that is, by any measure, deeply concerning, suggesting the path of this powerful system is unfortunately all too predictable. When multiple independent forecast models converge on a single, unusual outcome, it indicates an atmospheric signal so strong that it overrides the standard margins of uncertainty. The models are not hedging their bets. Their calculations all point toward the same event, a ridge of high pressure that is projected to move east while maintaining its intensity through the middle of the week. This strange persistence raises a deeper question, one that climate scientists have been urgently debating for over a decade. There is a growing body of evidence supporting a hypothesis, though it is still contested that the rapidly warming Arctic is reducing the temperature gradient between the poles and the tropics. This, in turn, may be slowing the Rossby waves, the immense atmospheric patterns that guide the jet stream and the weather systems that travel along with it. A slower Rossby wave could lead to a slower jet stream, making weather patterns like heat domes stickier and more resistant to moving on. It is important to state that this mechanism is not a definitive explanation for the current event. The science is genuinely uncertain, and embracing that uncertainty is key to understanding the situation honestly. However, what we can say is that the behavior of this ridge, its refusal to follow a typical life cycle, its structural reorganization instead of decay, is at the very least consistent with the kind of persistence this hypothesis would predict. Whether this is causation or mere coincidence is a complex question that attribution scientists will work on for months to come. But right now, we are witnessing the event unfold, and the pattern is acting precisely as a slowing jet stream would if the theory is correct. As this ridge amplifies and migrates, something else is developing underneath it. A phenomenon that the fire weather community is watching with a particular kind of dread, the kind that comes from recognizing a dangerous setup they have seen before. To understand the gravity of the situation, we must first look at what should be happening according to standard atmospheric behavior. When a ridge of high pressure reaches its peak intensity, it is expected to stop growing. At this zenith, the atmospheric dynamics that built the ridge, the convergence of air high above, the sinking and warming of that air, and the suppression of clouds, are in a state of equilibrium. From this peak, the normal progression is one of weakening. The energy that created the system begins to disperse, the atmospheric heights fall, and the entire pattern relaxes toward a more neutral state. This expected life cycle is a fundamental concept built into every standard forecast model and described in every atmospheric science textbook. The data we are seeing now, however, shows the precise opposite of this expectation. The 500 millibar geopotential heights, a standard meteorological measure for the intensity of a high-pressure ridge, have not been falling within the system's core. Instead, they have been rising. The observed and forecast numbers do not describe a system that is at its peak and beginning to decay. They describe a system that has already passed what most models saw as its maximum strength and is continuing to intensify. To put this in concrete terms, the 500 millibar level in a strong but normal heat dome over the southwestern United States at this time of year sits around 580 decameters. Current projections show this ridge approaching 588 decameters as it moves east, an intensity that is in the uppermost tier of what is physically possible for this region in late spring. While not entirely unprecedented, such values are typically seen only during the hottest part of summer, in July and August. To see these heights in early May is unusual, To see them actively increasing in a ridge that was supposed to be collapsing is something more. So, what is driving this anomalous amplification? The answer appears to lie in two reinforcing mechanisms that, in combination, create a particularly potent setup. The first is a process known as subsidence. As air sinks inside a high-pressure ridge, it descends into regions of greater atmospheric pressure and becomes compressed. This compression causes the air to warm, following the same thermodynamic principle that makes a bicycle pump feel hot after vigorous use. As this air descends for several kilometers, the compressional warming can add many degrees to its temperature, adding more energy to the system. This additional energy leads to higher geopotential heights, which means a stronger ridge, which in turn causes even more subsidence. It is a powerful, self-reinforcing loop that, once established, requires a significant external force to break. The second mechanism is solar amplification. A strong ridge naturally suppresses the formation of clouds. With no clouds to block it, the full power of the May sun, which delivers nearly its maximum annual energy at this latitude, reaches the surface. This intense surface heating further warms the lower atmosphere, which increases the pressure gradient and reinforces the ridge even more. The system is, in a very real sense, feeding itself. This concept of a system feeding itself is not merely a metaphor. It is a literal description of the atmospheric energetics at play. And it is here that we find the critical distinction for why this matters so deeply. An amplifying ridge is fundamentally different from one that is simply sustaining itself. A sustaining ridge maintains its current state, holding its ground. An amplifying ridge, however, is actively accumulating energy. And in the laws of physics, energy that accumulates must eventually go somewhere. It does not simply vanish. When the pattern finally breaks, all of that stored energy has to be redistributed throughout the atmosphere. And that process of redistribution can be a powerful and disruptive one. A broader, more speculative question hangs over these events, one that deserves honest consideration, even if the answers remain elusive. Climate scientists who study atmospheric dynamics have raised a compelling possibility that a warmer baseline atmosphere, where the entire column of air from the ground to the stratosphere holds more energy than it did a century ago, might enable heat ridges to persist and even strengthen for longer periods before they naturally dissipate. The warmer the air, the more energy is available to fuel the feedback loop of sinking, warming air. With more energy in the system, it can better resist the atmospheric forces that would normally break it apart. Is this what we are witnessing? In truth, we do not yet know. The science of attributing any single weather event to broader climate trends is a meticulous and time-consuming process. The researchers who perform this work rigorously are the first to caution that declaring one heat dome as definitive proof of a change in atmospheric mechanics requires far more data and analysis than the event itself can provide. However, we can observe that the behavior of this ridge, amplifying after its expected peak instead of weakening, is consistent with what a warmer atmosphere might theoretically produce. It is not proof, but it is a significant data point, one that aligns with a growing collection of others, all pointing toward a similar conclusion. The amplification of this immense ridge directly dictates the hazardous conditions developing beneath and around it. These consequences are not abstract. They include the dangerous fire environment that the National Weather Service in Bismarck is warning about, as well as the severe weather organizing along the system's eastern edge. A more powerful ridge creates a steeper pressure gradient along its periphery, resulting in stronger, more sustained winds. It also leads to a more thorough suppression of humidity across the regions it dominates, and the dry air it produces becomes more persistent. All these factors explain why this event is about much more than just high-temperature readings in Denver. It is a case study in what happens when a rare, self-reinforcing atmospheric system is given enough time and energy to reach its full potential. The most unsettling part, for forecasters and residents alike is that this system is still developing. The way weather forecasters communicate risk can tell a story of its own, and paying close attention reveals where their deepest concerns truly lie. When the primary threat from this system was heat, the forecast language was careful and serious, following the standard escalating structure used by the National Weather Service. The progression began with heat advisories, moved to excessive heat watches, and finally culminated in warnings as temperature projections became more certain. This is a language the public understands well, and it translates directly into actions taken by emergency management. In a sense, it represents the normal operational communication for a significant heat event. However, the language that soon emerged from the Bismarck Forecast Office was different in its very nature. It was not simply a further escalation of the concern over temperature. Instead, it signaled a shift in the entire category of risk being communicated. The new warning was for critical fire weather conditions expected to last for several days. That specific phrase carries a technical weight within the fire weather community that is worth exploring, as it explains why forecasters responded to this new setup with a tone that, when reading between the lines of official government bulletins, registered as something approaching alarm. The term critical fire weather conditions is not used lightly. It is a diagnosis that requires the simultaneous presence of several specific ingredients. The first is wind speeds that are elevated enough to drive the rapid spread of a fire, typically sustained in the range of 20 to 35 miles per hour, with even stronger gusts. The second is a relative humidity low enough to dry out surface fuels to the point of easy ignition and swift combustion, usually below 20 to 25%. Critically, the third factor is duration. These conditions must persist long enough for their combined effect to become a major threat. A single afternoon of marginal fire weather might warrant a watch, but several consecutive days where these criteria are met triggers a warning, a signal that an event with a very high probability of becoming a major fire is already taking shape in the atmosphere. The setup developing across the northern plains under this migrating ridge checks every single one of these boxes. The physics of the situation are as simple as they are alarming. The wind field associated with a strong ridge of high pressure is not static. The pressure gradient around the ridge's edges generates a persistent, organized flow of wind that, in a flat landscape like the plains, can sustain itself for multiple days without the typical overnight calm experienced in coastal or mountainous regions. At the same time, the relative humidity values forecast for North Dakota and the surrounding areas are projected to plummet into the teens during the peak afternoon hours. To put that number in context, the science of fire behavior uses relative humidity as a primary predictor because it directly governs the moisture content of fine fuels, the dry grass and small twigs that serve as the initial ignition point for most large wildfires. When relative humidity drops below approximately 25%, the moisture content of these fine fuels falls into a range where a single spark can have catastrophic consequences. Whether from a vehicle, a power line, a discarded cigarette, or a lightning strike, that spark can ignite a fire that, when driven by sufficient wind, will spread faster than any ground-based suppression team could possibly respond. This brings us to a final element that makes the current Northern Plains setup so distinctively dangerous, in a way that might not be immediately obvious if one's mental model of wildfire is based on the forest fires of the Pacific Northwest or the chaparral burns of Southern California. In early May, the Northern Plains are in what fire managers call the pre-green-up window. The region's vegetation, its native grasslands, agricultural stubble, and roadside growth has not yet produced the new, moist growth of the season. Instead, the dead material from the previous year, including cured grass stems, dried seed heads, and old crop residue, remains on the surface. This material is bone dry and extends for hundreds of miles without the natural fire breaks, like mountains and dense forests, that can help slow fires in western zones. Under these conditions, grassland fire behavior is fundamentally different from what most people visualize when they think of a wildfire. It moves with astonishing speed, in some cases dramatically faster than a person can run, even in relatively modest winds. With the sustained 20 to 35 mile per hour winds projected by the Bismarck forecast, grass fires can travel at speeds that make them genuinely impossible to outrun on foot, transforming the open plains into a landscape of immense and immediate peril. The immense atmospheric ridge building toward Colorado is not merely threatening temperature records that have stood for over a century, it is also generating an environment primed for fire. This reveals a crucial insight into the events unfolding before us. The record-breaking heat-scorching urban centers and the lethal dry winds sweeping across the open plains are not two separate, parallel phenomena. Instead, they are concurrent effects stemming from a single, powerful atmospheric system. The devastating Smokehouse Creek fire of 2024 offers a chilling portrait of this system's power. Consuming nearly 1 million acres in the Texas and Oklahoma panhandles, it became the second largest wildfire in American history, moving with a terrifying velocity that overwhelmed evacuation plans and defied the efforts of ranchers trying to save their livestock. Understanding that these events are two sides of the same coin is essential, as it means the geographic scale of the impact is far greater than any single temperature reading might suggest. This single atmospheric system is producing effects that are not only intense, but also profoundly out of season, a fact reflected in the official reactions of forecasters. In early May, red flag warnings are now active across parts of the northern plains, an event that is historically unusual. Typically, such warnings are clustered in the late summer and early fall, a time when months of drying have pushed fuels to their most volatile state, and the last of the monsoon moisture has retreated. To see the criteria for multi-day red flag warnings met in the first weeks of May suggests the system is arriving before the historical conditions for such fire risk have even developed. This raises an unsettling question. If the atmosphere is already producing this level of danger before the full heat of summer, before the landscape has fully greened up, and before other large-scale climate drivers have fully engaged, what might July and August hold? If this is our starting point in early May, where does the trajectory of this fire season ultimately lead? To better understand the gravity of the situation, we must first examine what forecasters are communicating, not just through their explicit warnings, but through the subtle yet significant evolution of their language. The National Weather Service, by design, does not engage in panic. This is not a flaw, but a foundational feature of the institution, essential for maintaining public trust. If a government agency responsible for safety communications used dramatic language for every unusual event, its most urgent messages would eventually lose their power. Consequently, the NWS employs a deliberately conservative and escalating scale of communication, progressing from a watch to a warning, and finally to an emergency, only when both the severity of an event and the confidence in the forecast cross specific, high thresholds. It is this very culture of restraint that makes the vocabulary currently appearing in their forecast discussions so profoundly telling. Within the lexicon of NWS forecast discussions, there exists a graduated scale of intensity, and forecasters ascend this scale only with increasing confidence. Terms like above normal signify a departure from the climatological average that is noteworthy, but occurs with some regularity. The phrase well above normal signals a more significant shift, an anomaly the forecaster wishes to highlight for special attention. But the term record-breaking occupies a different category altogether. It is not merely a matter of degree. It represents a declaration of confidence. It means the forecaster is willing to stake their prediction on the outcome that a specific, numbered record, one that has stood in the official data for years, is about to be broken. In the current discussions for Denver, Forecasters are not using cautious terms like potentially challenging records. They are using record-breaking in reference to a daily maximum temperature that has remained unbeaten since 1915. For temperature, this is the highest rung on the ladder of predictive language. However, the temperature forecast is only one part of the narrative being written in the sky. Alongside this language of extreme heat, the fire weather forecasts are communicating a parallel level of risk. The phrase, critical fire weather conditions, is more than a simple description of the weather. It is a formal declaration that a threshold has been crossed. It confirms that forecasted conditions meet or exceed the specific, stringent criteria the NWS uses to issue red flag warnings. These criteria are not arbitrary. They were established, and in many cases, revised upwards, in the wake of catastrophic events like the Marshall and Smokehouse Creek fires, which revealed that older thresholds were underestimating modern fire danger. These updated standards are designed to pinpoint the precise conditions most strongly correlated with uncontrollable, catastrophic fire behavior in the historical record. When these two distinct categories of language, record-breaking heat and critical fire weather, are used by adjacent forecast offices to describe the same atmospheric system over the same period, the message transcends the sum of its parts. It communicates that forecasters are observing a unified event that is simultaneously pushing the limits of extremity across multiple, interconnected domains of risk. This is not simply a heat wave happening to coincide with some breezy conditions. It is a singular, coherent atmospheric pattern that is generating top-of-the-scale risk in more than one category at the exact same time, a sign of a system operating at its maximum potential for danger. There is one final, subtle detail in the NWS forecast language that merits close attention, a phrase that carries immense weight within the meteorological community. The appearance of the words "several days" in the Bismarck fire weather discussion is doing profound communicative work. A typical red flag warning covers a brief window, usually a few hours or perhaps a day or two, reflecting an acute event like a frontal passage that brings temporary wind and low humidity. But several days describes something entirely different. It signals a sustained, unbroken period of elevated ignition probability, where the peak risk is not confined to a few dangerous afternoon hours, but is renewed for multiple consecutive days. From a fire management perspective, the difference between one dangerous afternoon and several is not linear. It is exponential. A single day is a crisis to be managed. A sustained period of critical conditions is a siege that can exhaust resources, overwhelm defenses, and change a landscape forever. With each passing day that these conditions endure, the opportunity for an ignition source, whether from nature or human activity, to spark a conflagration in a primed environment grows. There is a hidden insight embedded in the careful language of meteorologists, the compounding probability of disaster. This forecast language acts as its own early warning system, sounding an alarm long before the fires begin, before temperature records are shattered. And before the severe weather we will soon discuss erupts across the plains. The words within these official discussions offer a preview of the atmospheric state that forecasters see unfolding, and the picture they are painting is not of a manageable weather event that is merely more intense than usual. Instead, their language describes a system that is pushing the boundaries of multiple risk categories at once. It is a system that has persisted far longer than anticipated, and most critically, may be establishing a second phase of atmospheric organization, even more dangerous than the first. The quiet implication, though never stated explicitly, is that this atmospheric system is not yet finished with its work. The ridge that amplified instead of collapsing, that journeyed east instead of dissipating, and that is now generating record heat and critical fire weather from the same structure may also be fueling the conditions for what is to come. And where this ridge meets the stream of moisture flowing north from the Gulf of Mexico, the atmosphere is poised to do something that appears to be the very opposite of a heat wave. What that entails should be of just as much concern as everything we have explored thus far. To truly comprehend the threat, we must be precise about what critical fire weather means on a practical level, as the gap between its technical definition and public perception is where much of the danger resides. When most people hear the term, they think of dryness, and while aridity is a component, it is not the most decisive one. The single ingredient that fire behavior analysts consistently identify as the most dangerous, the one that separates a containable blaze from an uncontrollable one, is wind. This doesn't refer to extreme newsworthy gales, but rather a sustained wind between 20 and 35 miles per hour, combined with very low humidity. This specific pairing is what produces rates of spread capable of overwhelming suppression resources. It creates a scenario where human intervention becomes nearly impossible. In such a volatile environment, the wind becomes a multifaceted accelerator of the blaze. Its influence is not singular, but a cascade of effects. First, it rushes ahead of the flames, drying out the unburned fuel and preconditioning it for ignition before the fire even arrives. Simultaneously, it forces a constant supply of oxygen into the combustion zone at the base of the flame front, dramatically increasing the rate at which fuel is consumed and energy is released. The wind also acts as a carrier, lofting embers, sometimes called firebrands, far ahead of the main fire. These embers can travel hundreds of yards, or even miles, igniting new spot fires in areas the primary burn has not yet reached. Finally, it physically tilts the flame angle forward. This action drastically increases the fire's rate of spread on level ground and can multiply it by factors of 10 or more on upward slopes, creating a terrifyingly fast-moving wall of fire. At this moment, the northern plains exhibit all of these dangerous characteristics in abundance. The wind field created by the migrating ridge, as it settles over Colorado and the high plains, is generating a sustained southwesterly flow across the Dakotas, Nebraska, and Kansas. These winds fall squarely within the range that fire behavior charts describe as conducive to extreme spread conditions. Adding to this peril, humidity values forecasted to drop into the teens during peak afternoon hours will create a level of atmospheric drying that reduces the moisture in fine fuels to a bare minimum, meaning very little energy is needed for ignition. The final component is the fuel itself, a vast, uniformly distributed carpet of cured grassland from the previous growing season, all within the pre-green-up window we discussed earlier. This landscape stretches for hundreds of miles in some places, with no significant natural fire breaks to halt a fire's advance. It is vital to understand that this fire weather setup is not some unfortunate coincidence occurring alongside the heat dome. It is a direct and inseparable product of the same atmospheric structure. The very same ridge that is threatening a century-old temperature record in Denver is also the engine generating the powerful winds and intense drying that create this fire environment in North Dakota. The system did not follow its expected life cycle and collapse. Instead, it amplified and migrated. As it journeyed eastward, it carried its fire-generating capabilities with it, introducing this profound level of risk into a region that typically sees such conditions much later in the year and for shorter periods. This reveals the deeply interconnected nature of our planet's large-scale weather patterns. Just 2 years prior to this event, in February and March of 2024, the Smokehouse Creek fire burned across the Texas and Oklahoma panhandles under a similar convergence of factors. That fire, which consumed nearly 1 million acres before it was contained, became the second largest wildfire in recorded American history. It did not ignite under the blistering heat of July, but during a volatile winter to spring transition that brought the same deadly combination of cured fuels, persistent wind, and critically low humidity. The sheer speed of that fire's growth astonished even the most experienced firefighters in the country. It overran ranching operations before owners could evacuate their livestock and threatened communities that, by any reasonable historical assessment, were never considered to be in primary wildfire exposure zones. The current situation in the Northern Plains is not identical to the Smokehouse Creek event. The specific geography is different. The potential ignition sources are unknown, and every forecast carries its own range of uncertainty. However, the fundamental meteorological pattern, the combination of sustained wind, critically low humidity, pre-green-up fuel conditions, and multi-day persistence originates from the same family of atmospheric setups. The official forecast discussion from Bismarck is describing precisely this. Not a fleeting moment of danger, but several consecutive days under the influence of this high-risk atmospheric family. What makes this particular moment so significant is the immense geographic scope of the risk. The fire environment on the plains is not organized into the discrete, predictable zones often seen in western forests, which have known canyon systems, established spot fire corridors, and vulnerability maps developed over decades of experience. The plains, by their very nature, extend broadly and continuously. The danger is not confined to a specific valley or mountainside. It is a vast, unbroken landscape, which suggests that any fire that begins could have an equally vast and unbroken path to follow. This changes the very nature of the threat, making it more diffuse and, in some ways, far more daunting. Across vast stretches of the landscape, the fuel for a fire lies in wait, remarkably consistent. Nestled within these expanses are small, isolated communities, distant from the major resources needed to combat a blaze. Their reliance on road networks creates a profound vulnerability, as a rapidly advancing fire could sever escape routes before evacuation orders are even issued. This is the precise vulnerability now being activated by a persistent fire weather pattern. Originating from a high-pressure ridge that was predicted to dissipate but has instead intensified, the story is not merely the heat or the fire risk alone. The crucial element is that a single, unexpectedly resilient atmospheric anomaly is generating both conditions at once, making this moment in American weather one deserving of close attention. To understand this risk, our focus shifts to Colorado's Front Range. For locals, the term is second nature, but its true significance is often best seen from afar. This corridor is a ribbon of cities tracing the eastern flank of the Rockies, including Denver, Boulder, and Colorado Springs, along with suburbs that have flourished in recent decades. Home to 5 million people, it is the most populous region in the Mountain West. Critically, it sits at the exact meeting point of urban expansion and a natural landscape whose terrain can fuel the nation's most dangerous fire behavior. It raises the question of how we reconcile human settlement with the inherent risks of the natural world. This reassessment of risk was forged in the aftermath of the Marshall Fire on the 30th of December 2021. Ferocious downslope winds, with gusts over 100 miles per hour, combined with plummeting humidity to transform a Boulder County suburb. Seemingly benign landscapes, cured grasses, lawns, and green spaces became a continuous fuel bed. The fire swept through a community previously deemed low risk, incinerating nearly 1,100 homes in hours. Residents had only minutes to flee, and for some, escape routes became impassable almost instantly. The Marshall Fire was a tragic lesson that the boundary between safe suburbia and wildland fire was far more permeable than imagined. Subsequent analysis by scientists revealed a sobering truth. The meteorological conditions were not a complete anomaly. They represented a known atmospheric pattern in the Front Range, but its potential for catastrophic fire had been systematically underestimated. Risk assessments were based on a history that lacked a disaster of this scale, creating a critical blind spot. In response, National Weather Service offices in Colorado revised their red flag warning criteria. They adjusted wind and humidity thresholds to flag such an event as it forms, not merely in retrospect. It is precisely these updated, more sensitive thresholds that are now sounding the alarm. The current weather pattern, driven by the migrating ridge pushing temperatures to record levels, is producing the exact combination of high winds and intense drying that the new criteria were designed to detect. This confirms the system is working as intended, but it also confirms the present danger is very real. In Colorado's Front Range, the urban-wildland interface is not a simple line, but a vast zone of interpenetration. Housing developments push into canyons and across grasslands, a reality of where population has expanded over 30 years. Millions now reside where, given the right conditions, a wildfire could reach their homes within minutes. This is not exaggeration, it is a statement of geography. The amplified ridge now moving toward Colorado carries the dangerous pairing of wind and dry air that the new warnings are built to identify. A record temperature in Denver is noteworthy, but a hot day with powerful winds and single-digit humidity at the edge of a metropolis presents a profoundly more dangerous scenario. All these threads converge on a single narrative. The high-pressure ridge that persisted beyond its expected life is doing more than breaking records. It is imposing a tangible, measurable risk upon distinct populations from the Colorado Front Range to the Northern Plains grasslands. This is the profound, real-time impact of a single atmospheric system deviating from its predicted path, a reminder of how one anomaly can have far-reaching human consequences. As this system tracks eastward, it highlights a significant imbalance in how wildfire risk is managed in the United States, with direct implications for North Dakota and Montana. The nation's wildfire infrastructure, air tankers, hotshot crews, command structures, and detection systems, was largely forged in response to fires on the Pacific coast and in the Mountain West. This is where dramatic fires have historically captured attention and driven resource allocation. These are the regions where decades of fire history have yielded detailed maps for predictive modeling, and where affected communities have had the political and media influence to ensure their needs are met. By almost every one of these measures, however, the Northern Plains represents an entirely different world. It operates under a different fire regime, with risks that do not always fit the models and response strategies developed for Western forests. It is a landscape that exists, in many ways, outside the primary focus of the national wildfire conversation, creating a unique and often overlooked vulnerability. The fire that threatens this landscape is a grassland fire, a phenomenon that moves with a speed and suddenness that can eclipse even a forest fire under the same wind conditions. Here, the resources available for suppression are spread thin across vast distances. The robust interagency coordination that defines emergency response in the western states finds only a weaker echo in the Dakotas and eastern Montana. In this environment, communities are often small agricultural towns and isolated ranch operations scattered across a terrain where a fire, propelled by 30 mile-per-hour winds, can race from a distant horizon to a property line in mere minutes. This reality is not hypothetical. North Dakota's recent history is marked by major fire events. During dry years, driven by the very combination of wind and low humidity building now, these fires have inflicted catastrophic damage on the agricultural economy. They have consumed hundreds of thousands of acres of rangeland essential for grazing, and have sometimes resulted in the loss of human life and livestock tragedies that rarely captured national attention, as the media's focus on wildfires often mirrors the geography of major media markets. The warning from the Bismarck Forecast Office, speaking of several days of critical fire weather, points to a duration that dramatically elevates the probability of a major ignition. Each passing day introduces another cycle of peak risk, another stretch of afternoon hours where high winds and low humidity can turn any spark into a rapidly spreading blaze. But each day also adds another layer of fatigue for fire managers, whose resources are already stretched before the event has even reached its full potential. The true significance of this situation, however, lies in its origin. The northern plains are not facing this threat because of some separate, coincidental weather system. This peril is a direct consequence of the same atmospheric ridge that was predicted to collapse after the initial phase of the May 2026 heat dome. Instead of weakening, it amplified and migrated eastward. The very structure threatening to break a Denver temperature record from 1,915 is also the engine generating the multi-day wind and drying event, activating a high-consequence fire environment across a region that receives only a fraction of the resources directed toward more high-profile fire zones. This imbalance between the geographic scale of the risk and the distribution of resources is a story in itself, but it is a downstream effect of the atmospheric narrative we must follow. And that narrative, it seems, is far from over. So much of our public conversation around extreme weather is centered on peak values, the single highest temperature, the most powerful wind gust, the record-breaking rainfall total for an hour or a day. These peak values are compelling because they are concrete and easily measured. They fit neatly into a headline, making them simple to communicate and understand. But what if this focus on a single dramatic number misses the more profound danger? A growing body of research from fire science, heat, health, and atmospheric dynamics suggests that in many contexts, the duration of an event is a more critical variable than its peak intensity. The unfolding weather pattern offers a perfect case study in why this is so. Let us first consider the fire risk. A single afternoon with winds at 30 miles per hour and relative humidity at 15% is undeniably dangerous. Under such conditions, a fire that ignites around noon has several hours to burn under peak conditions before the natural moderation of evening, with its decreasing winds and rising humidity, begins to take effect. This scenario, while acute, has a predictable temporal structure that allows response systems to adapt. Suppression resources can be staged, air support can be prepositioned, and evacuations can be initiated for the most vulnerable communities. Now, imagine several consecutive days under these same conditions. On the first day, the acute response framework is still effective. By the second day, however, the situation has changed. Any resources committed to fires that started on day one are now partially consumed. Crews are growing tired, and aircraft are cycling through necessary maintenance. If no major fire ignited on the first day, a subtle temptation to relax may emerge, a feeling that the crisis did not materialize as scheduled. By the third day, the compounding effect of multiple days without humidity recovery means the fuel moisture has continued to drop. The grasses and shrubs are now substantially drier than they were even at the peak of day one. This is the crux of the matter. Even if the meteorological conditions on the third day are slightly less intense, the probability of a catastrophic ignition is actually higher. The cumulative drying has pushed the fuel conditions deeper into a critical state. This is the duration multiplier, one of the most vital yet least understood concepts in communicating fire weather risk. The Bismarck forecast's language of several days is not merely describing a longer version of a single-day event. It is describing a qualitatively different risk environment, one where the cumulative probability of a major fire compounds daily, even as the capacity of fire management systems is steadily eroded by the sustained demand. This same principle of duration applies, in a different but equally critical way, to human health during a heatwave. A single day of extreme heat can be lethal, primarily causing heat stroke in vulnerable populations like the elderly, the very young, and those with pre-existing medical conditions. Public health systems and emergency services are largely designed to respond to these acute events by activating heat health plans, opening cooling centers, and increasing welfare checks. But multi-day heat events cause fatalities at rates that far exceed what an analysis of single-day peaks would predict. The reason for this is the importance of overnight recovery. Human physiology relies on nighttime temperatures dropping sufficiently to allow the core body temperature to return to normal before the next day's heat load begins to accumulate. When a persistent atmospheric ridge keeps overnight lows elevated, suppressing the radiation of heat into space, that crucial recovery cannot happen. The physiological burden compounds. An individual who might have survived a single day of peak heat, thanks to some capacity for overnight recovery, can instead experience a dangerous accumulation of heat stress over multiple days and nights, when that opportunity for relief never comes. The persistence of a weather pattern over time introduces another dimension to its impact. A ridge of high pressure that remains in place for days is not merely holding its ground, it is performing cumulative work on the column of air beneath it. This process drives continuous subsidence, leading to greater compressional warming, more intense surface heating, and increased evapotranspiration from the soil and vegetation. As this continues, the land surface progressively dries out. The soil's capacity to store heat diminishes, and the plant life in the region experiences escalating thermal stress. All of these factors combine to alter the energy budget at the interface between the land and the atmosphere. This raises a profound question. Can these changes feed back into the atmospheric pattern itself, helping the ridge to sustain its own existence? This brings us to an idea that resides on the frontier of climate science, a concept that is speculative and genuinely uncertain, yet too significant to overlook in an honest assessment of this ridge's unusual behavior. There is a potential mechanism that climate scientists began to investigate with urgency following the fire seasons of 2020 and 2021, when the duration and scale of Western wildfires reached levels unseen in the modern observational record. The mechanism involves smoke, and if it is indeed real and at play in the current situation, it would represent a feedback loop that most operational weather forecasting systems are not yet able to fully capture. This suggests a potential blind spot in our predictive capabilities. The fundamental principle is this: when a massive wildfire generates a substantial amount of smoke, that smoke is not an inert bystander in the atmosphere. It actively scatters and absorbs incoming solar radiation, which in turn diminishes the amount of energy that can reach the surface beneath the smoke layer. With less solar input at the ground, there is less surface heating. Ordinarily, this would tend to weaken a surface high-pressure system, which might seem like a process that would help break down the ridge. The mechanism, however, is far more intricate than this simple cause and effect would suggest. The complexity arises because the smoke layer is also altering the atmosphere's vertical temperature structure, otherwise known as the lapse rate. By reducing the solar energy reaching the surface while the smoke itself absorbs and radiates heat at mid-levels, it can forge a more stable atmospheric column. This is a state where the temperature decreases less rapidly with altitude than it normally would. A more stable column strongly resists convective, overturning the very process that helps break down heat domes through the eruption of deep thunderstorms, which mix cooler air downward and disrupt the pattern of sinking air. If smoke is stabilizing the column and suppressing the convective instability that would otherwise challenge the ridge, then a ridge that generates fires could, through its own smoke, be actively extending its own lifespan. While this mechanism is still the subject of early research, it is grounded in real-world observation. Scientific papers published after the 2020 fire season, which analyzed atmospheric data from that historically unprecedented year, uncovered evidence that smoke from major Western fires exerted measurable effects on surface temperatures and the structure of the boundary layer, effects that operational weather models had failed to predict. These were not minor discrepancies that could be dismissed. The data revealed real signals indicating a feedback loop operating on a scale large enough to influence regional atmospheric circulation. It remains an open question whether this feedback is active in the present situation. The fires that could develop under the current weather setup have not yet ignited, and smoke feedbacks depend on a substantial loading of smoke in the atmosphere, which requires large fires burning over a sustained period. However, the scenario that is building several days of critical fire weather across the northern plains and an elevated risk along the Colorado Front Range creates a situation where substantial smoke production is a plausible, near-term outcome. Should these fires develop and the smoke loading increase, the question of whether that smoke is altering the atmospheric column in ways our models aren't capturing will become operationally relevant, not just a point of scientific interest. What this all illuminates is a fundamental truth about our planet's climate. The atmosphere is not a simple, linear system where a given cause produces a predictable effect, and where feedback loops are either well understood or can be safely ignored. It is a complex, non-linear system where the behavior of a ridge beyond its expected life cycle might be shaped by mechanisms that forecast models were not designed to capture. It is possible that these very mechanisms are making the current event more persistent, more self-sustaining, and ultimately more difficult to accurately forecast than standard model guidance alone would indicate. This is not a reason to dismiss the model guidance. The strong agreement among the ensembles we discussed earlier, the high confidence in the ridge's trajectory and intensity from both American and European models is both real and meaningful. It is, however, a reason to interpret that guidance with an appropriate sense of humility, particularly at the outer edges of the forecast window. This is where uncertainty naturally grows, and where such non-linear feedbacks have the most time to accumulate and assert their influence. And something is already taking shape on the eastern edge of this ridge that the models are just beginning to resolve. What they are seeing is not more heat, but something else entirely, something the atmosphere creates when pressure, moisture, and instability converge along a sharp boundary. It is the other face of the very system we have been tracking. Every powerful ridge, it turns out, possesses two distinct faces. The one that captures everyone's attention is the one directly beneath it, where sinking air, compression, and clear skies generate record-breaking heat. But the other face, located on the eastern edge of the ridge, where it meets the downstream atmospheric pattern, is where something fundamentally different unfolds. In the current setup, that something different is a phenomenon that the Storm Prediction Center watches with the utmost seriousness. The eastern boundary of a strong high plains ridge is a zone where atmospheric dynamics converge in a manner that is almost a mirror image of what is happening under the ridge's core. While air under the ridge is sinking, stabilizing, warming, and drying, the air along its eastern edge is doing the opposite. It is rising, destabilizing, and cooling aloft, all while encountering an enormous supply of low-level moisture streaming northward from the Gulf of Mexico, carried on the southerly flow circulating around the high-pressure system. By the month of May, the waters of the Gulf of Mexico have grown warm, sufficiently so to fuel a remarkable flux of moisture into the southern and central United States, especially under an unusually strong, high-pressure ridge. Ahead of this powerful western ridge, a southerly wind develops that functions as a vast pump, drawing moisture from the Gulf northward, across the southern plains, and eventually toward the upper Midwest. This process loads the lower atmosphere with the abundant moisture that is a critical ingredient for severe weather. A dramatic confrontation occurs when this moisture-laden air mass encounters the dry line, a sharp boundary separating it from the arid continental air advancing from the desert southwest. In just a matter of hours, this clash can cause atmospheric instability to build to tremendous levels. Meteorologists quantify this instability using a metric known as CAPE, or convective available potential energy, which measures the energy available to an air parcel if it is lifted and starts to rise on its own. In typical severe weather scenarios, CAPE values between 2,000 and 3,000 joules per kilogram are considered significant, capable of fueling powerful thunderstorms. The current pattern, however, combines intense surface heating from the ridge, deep moisture from the Gulf, and strong wind shear, leading models to project CAPE values in the highest tier of what the southern plains ever experience. Yet, there is a more troubling dimension to this atmospheric pattern, one that elevates it beyond a routine severe weather setup. The very same ridge responsible for amplifying the heat and fire risk is also organizing the wind shear along its eastern edge. This creates an environment ripe for rotating thunderstorms, known as supercells, which are the storm type most directly linked to significant tornadoes, destructive hail, and damaging straight-line winds. The directional shear, the change in wind direction with altitude associated with such a strong western ridge, is highly conducive to storm rotation. This raises a critical question. How is one atmospheric feature creating such different, yet equally dangerous, threats? In their forecasts for Oklahoma and Texas, the Storm Prediction Center is now using language that, much like the fire warnings from Bismarck, resides in the upper echelon of their alert system, signaling a setup of exceptional concern. These two phenomena, record-breaking heat and critical fire conditions under the core of the ridge, and the ingredients for a major severe weather outbreak along its eastern flank, are unfolding in unison. This simultaneity is no accident. It is a fundamental structural feature of powerful migrating ridges in the high plains. The same pressure gradient that drives subsidence and warming beneath the ridge also generates the southerly flow ahead of it, which acts as the moisture pump. Consequently, a stronger ridge creates a more powerful moisture pump, and a more powerful pump makes more energy available for storm development along the system's eastern boundary. Because the ridge has amplified far beyond its expected peak, it is directly magnifying the potential for severe weather downstream. The two systems are inextricably linked, two faces of a single atmospheric anomaly that has defied its expected life cycle. To truly grasp the potential of this event, we must look beyond the surface-level forecasts and into a deeper dialogue unfolding among meteorologists, a conversation that rarely reaches public weather coverage. This is partly because it involves a level of atmospheric dynamics that is difficult to convey in a short segment, and partly because it requires acknowledging a complexity that resists the simple narratives often used in weather reporting. This discussion centers on a fundamental process: the way a heat dome stores vast amounts of atmospheric energy and, eventually, releases it. This is the story of an unseen transfer of energy, a process that sets the stage for what comes next. Under a heat dome, the atmosphere is actively performing work. The process of subsidence compresses the air, causing it to warm significantly. Simultaneously, the suppression of cloud cover allows solar radiation to heat the ground with maximum efficiency. All the while, the persistent blocking of the typical west-to-east flow of weather prevents this thermal energy from dispersing, allowing it to accumulate in one region over an extended period. This raises a fundamental question. Where does all that accumulated energy go? It cannot simply vanish when the ridge finally weakens. Instead, the stored energy is redistributed along the boundaries of the system. The sharp gradients that form between the extremely hot, dry air under the ridge and the much more unstable, moist air along its eastern edge become the primary channels through which this energy is finally discharged. When the ridge eventually begins to break down, or as its eastern edge pushes into the Gulf air mass, the immense instability that has been building does not simply fade away. All the ingredients, the enormous CAPE values, the moisture-saturated lower atmosphere, and the organized wind shear do not politely wait for conditions to become merely favorable. Instead, the stored energy can be unleashed with explosive force. A useful analogy here is that of a pressure vessel. A heat dome acts like a container for atmospheric energy. As long as the rigid, high-pressure cap remains intact, the energy continues to accumulate inside. But when that cap weakens, or when its boundary becomes dynamically active, the resulting release of pressure can be incredibly fast, powerful, and widespread. While not every breakdown of a heat dome leads to a significant severe weather outbreak, the historical record reveals a compelling link between the collapse of amplified heat domes over the high plains and the subsequent formation of major severe weather events along the ridge's retreating eastern edge. This is the very pattern that the Storm Prediction Center is beginning to highlight in its extended range outlooks for the period between May 18th and May 23rd. The signals emerging in model guidance for that window show the kind of pattern reorganization that has historically preceded large-scale outbreaks. The energy that could fuel these potential storms, fed by weeks of heat dome amplification, rather than a more typical, shorter buildup, is immense. This is the critical energy transfer that most weather coverage overlooks. The heat dome is not just a story about heat. It is a preloading of the atmosphere's energy reserves, profoundly shaping what is to come. The potential intensity of any severe weather that follows the eventual collapse of this atmospheric ridge is directly related to the energy it gathered during its unusual amplification. A ridge that has lingered longer and grown stronger than anticipated has, in effect, wound the atmospheric spring more tightly. When that tension finally breaks, the release of energy is proportionally more powerful. This brings us to a developing signal for the period between May 18th and May 23rd. The latest model guidance is beginning to reveal a pattern that warrants careful discussion, both for what it suggests and for the significant uncertainty that still surrounds it. In the time frame centered on May 18th through the 23rd, both the American and European forecast models are pointing toward a major reorganization of the atmosphere. The ridge, currently migrating east and strengthening over the high plains, is projected to collide with an incoming trough from the Pacific Ocean. This interaction represents a potential external force, the very mechanism that could finally disrupt the ridge's anomalous persistence. However, the way a powerful ridge and an approaching trough interact is rarely a simple, clean process, especially when the ridge is as amplified as this one appears to be. It raises the question of what happens when such immense systems meet. When an energetic trough system encounters a highly amplified ridge, one possible outcome is that the trough fails to simply displace the ridge eastward. Instead, their collision can act as a catalyst, generating an entirely new low-pressure system. This surface cyclone would form along the boundary between the two clashing air masses, complete with its own distinct wind field, precipitation patterns, and potential for severe weather. The ultimate character of this potential cyclone, its strength, its trajectory, and its ability to tap into the vast reservoir of moisture and instability that has been pooling ahead of the ridge, will determine whether the May 18th to 23rd window is a routine transition or something far more dynamic. At this range, the forecast models have not yet reached the kind of consensus that would allow for high-confidence statements about specific severe weather events. Key variables, such as the exact arrival time of the trough, the precise placement of the developing surface low, and how the storm track will interact with the moisture field, all carry substantial uncertainty at a 1-0-day forecast horizon. This uncertainty is not a flaw in the models. It is an honest reflection of atmospheric predictability. Therefore, anyone claiming to know specific outcomes for that period is likely overstating what the data can truly support. Despite the uncertainty in the details, the ensemble guidance is in broad agreement on the overarching narrative. Something significant is poised to occur within the May 18th to 23rd window. The atmospheric pattern is set to reorganize, and this shift will unfold within an environment that has been preloaded with an exceptional amount of energy, a direct consequence of the anomalous ridge we have been tracking. This is not a typical late spring pattern change. The stage is set for something more. In atmospheric dynamics, there is a concept known as momentum, and it has a meaningful application here. Once the jet stream settles into a particular configuration, its own flow dynamics tend to maintain that pattern for a time, even after the original forcing mechanism starts to fade. A ridge that has been intensely amplified for a prolonged period can leave behind an imprint on the downstream flow, a lingering tendency toward ridging that can persist even as the original feature weakens. If this pattern possesses that kind of momentum, the reorganization around May 18th may not signal a clean return to normalcy. It could instead mark a transition into a new and perhaps equally unusual atmospheric phase. This possibility leads to a critical question that must frame our understanding as we continue to observe this system. It is a question without a clear answer yet, but one that gains urgency the longer this pattern holds. Are we witnessing a singular, anomalous weather event that will eventually dissipate and allow conditions to return to a more typical state? Or are we in the opening chapter of an atmospheric season that has undergone a fundamental shift in character? The answer to this question is directly tied to two other pieces of data that may be the most important in this entire narrative, though they are not about this week's forecast at all. Before we explore those larger data points, another immediate consequence of this system demands attention, as it is quietly altering the timeline for one of the West's most critical environmental variables, the snowpack. This is where the story of the heat dome connects to the silent acceleration of the fire season. The western United States is profoundly dependent on its mountain snowpack, which functions as its primary water storage system. Winter and spring precipitation accumulates as snow across the Sierra Nevada, the Cascades, the Rockies, and other ranges, melting slowly through the spring and early summer. This gradual release of water is what sustains the region through its dry months. The timing of this melt is a crucial regulator, controlling when vegetation in high elevation and transitional zones begins to dry out. This, in turn, dictates precisely when those landscapes become receptive to fire. The same heat dome responsible for record temperatures in places like Denver is also affecting the regional snowpack in a way not captured by immediate fire weather warnings, yet it will have consequences for fire risk over a much longer horizon. The unseasonably high temperatures sweeping across the mountain west in early May are dramatically accelerating the rate of snowmelt. The snow that had accumulated across the southern Rockies, in the ranges of Colorado and New Mexico, is now melting far earlier than it would under normal conditions. This premature melt releases its water much faster than the soil and vegetation can absorb it. The result is a reduction in the water supply available to keep vegetation moist through the summer, effectively advancing the seasonal transition to fire-receptive conditions well ahead of the historical average. An earlier start to this drying process does not necessarily guarantee that the peak of the fire season will be worse. Other factors, such as the development of the summer monsoon, the amount of moisture carried over in the soil, and the evolution of the El Nino Southern Oscillation (ENSO) pattern, will all shape peak season conditions. However, an earlier beginning means a longer total duration during which the landscape is vulnerable, all other things being equal. A longer fire season is a more dangerous one, simply because it provides a wider window of time for large ignition events to occur. A vast ridge of high pressure, responsible for shattering temperature records a century old, is also having a quieter, yet equally profound impact. It is extending the western fire season by weeks. This is a consequence that may not appear in immediate weather forecasts, but its mark will be indelible on the fire weather archives when we analyze the summer of 2026 inches hindsight. Beneath this atmospheric drama, a deeper issue comes into focus. A fundamental mismatch we can call the human system lag. To truly understand what this weather event reveals about our atmosphere, we must first acknowledge this disconnect. Consider the vast network of systems designed to manage weather risk across the United States. This includes the design assumptions for our power grids, the building codes for homes in fire-prone areas, and the complex water supply contracts that allocate this vital resource. It also encompasses the emergency protocols for evacuations and the insurance models that calculate risk and determine the cost of coverage. Every one of these critical systems was built upon a foundation of historical climate data, a library of past events once thought to be a reliable predictor of the future. They operate on assumptions about the nature of extreme weather, its frequency, its intensity, and its likely impact, all derived from the recorded patterns of the past. The central problem, however, is that this historical guide is now dangerously out of date. The distribution of risk has changed. As climate scientists have documented with growing certainty, the intensity and frequency of extreme weather events have shifted, and this rate of change seems to be accelerating, not stabilizing. Consequently, the vast infrastructure built for the climate of the 1970s or 1980s, which accounts for a significant portion of the American built environment, is now regularly facing conditions that exceed its original design. Parameters, meaning the maximum heat, wind, or rain it was engineered to safely withstand. This current weather event, the ridge that strengthened instead of dissipating, offers a live demonstration of this mismatch. As it threatens century-old temperature records and creates critical fire weather for days on end, the strain becomes visible. Fire management resources, budgeted for a traditional fire season, are already being pushed to their limits in early May. Power grids are activating demand management protocols long before the typical peak heat of summer. And in the affected regions, water utilities are struggling to manage reservoir levels and distribution pressures under conditions that are far from the seasonal norm. This delay between the rapid pace of atmospheric change and the much slower pace of institutional adaptation isn't the fault of any single decision or system failure. It is, rather, the predictable outcome when complex infrastructures which require decades to plan, fund, construct, and update are confronted with environmental shifts happening over the course of just a few years. The atmosphere is simply changing faster than our institutions can keep pace. It is in this widening gap, a void between the statistical assumptions our world is built on and the dynamic reality of our current climate, that the most severe consequences of extreme weather are found to accumulate. Whenever a heat dome migrates across the central United States, threatening records that have stood for a century, the comparison to the year 1936 is inevitably raised. There are indeed striking similarities between that historic event and the present one that merit careful examination. However, there are also profound differences that make a direct comparison far more complex than it first appears. The North American heat wave of 1936 stands as one of the most devastating weather events in the nation's recorded history. Taking place during the Dust Bowl, that summer brought temperatures to the Great Plains and Midwest that set records in numerous states, some of which remain unbroken. The atmospheric pattern responsible was a powerfully amplified ridge that moved across the continent's center, a setup that bears a strong family resemblance to what we see today. It was persistent, it intensified, and it broke records of a similar vintage. Yet, the world beneath that 1936 atmosphere was fundamentally different, making any direct comparison a delicate task. At that time, the soil moisture across the plains was catastrophically low after years of relentless drought. This was exacerbated by dryland farming methods that had stripped away the native sod, the very layer that once held soil and moisture secure. These human-driven factors of the Dust Bowl created a parched landscape that made it far easier for the atmosphere to generate and retain extreme heat. Indeed, some climate historians propose that these land surface feedbacks in 1936 were just as responsible for amplifying the heat as the atmospheric pattern itself. In 2026, the soil moisture conditions in the affected areas are different. While by no means better than the recent historical average, they are improved in some places compared to the dire state of 1936. This contrast forces us to confront a profound and scientifically uncertain question, one that sits at the heart of modern climate science. If the current atmospheric pattern can produce record-breaking heat comparable to 1936, but times without times the powerful land surface amplification that defined that event, what does this imply? It raises the unsettling possibility that the atmosphere itself has become more energetic, more adept at creating and sustaining extreme patterns than it was 9 decades ago. And if that is the case, what does it suggest about the potential for extreme weather in the months and years ahead? The answer is not yet known, but the question itself is of critical importance for our future. Sometimes, a single number can tell a story of profound change. That number is 2. In just the first half of 2026, the United States has experienced 2 separate events that climate scientists classify as 500-year heat events. The first occurred in March of 2026, when a heat dome sent temperatures soaring across the southern states, seriously threatening long-standing records and creating significant fire weather concerns before it finally dissipated. The second is the event unfolding now, the May system that intensified instead of weakening. It is currently challenging a Denver temperature record set in 1915 and has triggered critical fire weather warnings across the northern plains for multiple days. The phrase 500-year event requires careful unpacking. This statistical label is crucial, but because it is so routinely misunderstood, its misinterpretation can lead to one of 2 opposite and equally unhelpful errors in thinking. There is a common misunderstanding of what a 500-year event truly signifies. The term seems to suggest an occurrence that happens only once every 5 centuries, implying a long period of safety after one has passed. However, this interpretation is not what the data tells us. A 500-year event is, in reality, an event with an annual probability of 0.2%. This figure is derived from the historical frequency of events of a similar magnitude in any given year. There is a 1 in 500 chance of such an event taking place, and crucially, that probability resets each year, independent of the last. While the likelihood of 2 such events occurring in the same year by chance is exceptionally low, it is not a physical impossibility. When we witness 2 500-year class events within a single year, particularly in the same country and under a similar meteorological context, simple statistics begin to feel like an insufficient explanation. The more compelling possibilities are that the underlying probability itself has changed, meaning the climate has shifted to make these events more frequent than historical records would indicate, or that a common forcing mechanism is driving both events. In the current situation, it is plausible that both of these explanations are at play simultaneously. The idea that the fundamental probabilities have shifted is something that climate attribution science has been rigorously documenting for more than a decade. The scientific literature on heat events, in particular, is among the most robust in the entire field. Numerous independent research groups, employing a variety of different methods, have consistently reached the same conclusion. Extreme heat events that were once genuinely rare in a pre-industrial climate are now happening with frequencies that are 1 to 2 orders of magnitude higher. An event that might have had a 1 in 1,000 year chance of occurring in the climate of the mid-20th century could now be a 1 in 100 year occurrence. Similarly, what was once a 1 in 100 year event may now happen once per decade. The entire distribution of weather possibilities has shifted, and the extreme tails of that distribution, where the 500-year events reside, have shifted along with it. This raises a sobering question. Are our historical benchmarks for what constitutes a rare event now dangerously out of date? The second factor, a common forcing mechanism, connects directly to the broader climatic context of 2026. Both the March event and the current May event are unfolding within an atmospheric environment already being shaped by a developing climate pattern. This pattern has not yet achieved its maximum forcing potential, but it is already powerful enough to be pushing the atmospheric baseline toward conditions that favor extreme heat. This pattern is what climatologists refer to as El Nino, and the version currently developing in the equatorial Pacific is no ordinary one. Part 18. The ENSO problem. The timing is wrong. To grasp the gravity of the situation, we must first establish what a super El Nino means as a physical climate driver, and then explore why the timing of these recent events is the most alarming part of the entire picture. The timing is not a secondary detail. It is the central thread of this story within a story. Once this becomes clear, the two 500-year heat events that have already struck the United States in 2026 cease to look like mere bad luck. Instead, they begin to resemble something far more structured and considerably more concerning. El Nino represents the warm phase of a coupled ocean-atmosphere oscillation that occurs in the tropical Pacific. While the phrase coupled ocean-atmosphere oscillation may sound technical, the concept it describes is quite elegant. It suggests that the tropical Pacific Ocean and the vast expanse of air above it are intertwined in a slow, multi-year dance. Under neutral or normal conditions, the trade winds consistently blow from east to west across the equatorial Pacific. This action pushes warm surface water toward Indonesia and Australia. In its place, cooler water from the deep ocean is allowed to upwell along the coast of South America. This is the baseline state, the system's normal rhythm. But when something disrupts this delicate balance, the entire pattern begins to change. If the trade winds weaken, a process which is itself influenced by earlier ocean temperature anomalies, the massive pool of warm water that was being held in the western Pacific begins to slosh back toward the east. As a result, the eastern and central equatorial Pacific becomes significantly warmer, and this warming of the ocean changes everything in the atmosphere above it. When the sea surface temperatures in the central and eastern equatorial Pacific rise above their climatological average, the pattern of tropical convection undergoes a dramatic shift. These deep thunderstorm systems are the primary engine of the global atmospheric circulation, and their location is critical. The thunderstorms that were once clustered over the western Pacific and the islands of the maritime continent begin to ignite over the central and eastern Pacific instead. This geographic shift in where the atmosphere receives its most intense tropical heating sends waves of disturbance propagating outward. Specifically, it generates large-scale atmospheric waves known as Rossby waves. These waves travel into the higher latitudes, systematically altering the jet stream patterns over North America, Europe, and Asia. It is a powerful reminder of how interconnected our planet's systems truly are. The result of this large-scale wave propagation is a phenomenon climate scientists call teleconnections. These are the statistical relationships between the intensity of El Nino warming in the tropical Pacific and specific, predictable weather anomalies in regions located thousands of miles away. A strong El Nino, for instance, tends to create a particular jet stream configuration over North America. This typically leads to wetter and cooler than normal conditions across the southern tier of the United States, and warmer and drier conditions across much of the northern tier during the winter. It also tends to suppress Atlantic hurricane activity, while enhancing it in the eastern Pacific. Elsewhere, it can drive drought across Australia and trigger flooding in parts of South America. These teleconnections are among the most well-established and skillfully forecast relationships in all of seasonal climate prediction. They are not theoretical, they are real, documented across numerous El Niño events in our observational record. The magnitude of these effects scales with the intensity of the El Niño forcing in the tropical Pacific. This brings us to the term Super El Niño, and it is vital to understand what we are truly talking about when we use this phrase. Super El Niño is not an official meteorological classification, but rather a term used to describe an event of unusual and powerful intensity. The term Super El Niño is not merely dramatic language. It is a specific designation that climate scientists reserve for events of exceptional power. This label is applied when sea surface temperature anomalies in a critical monitoring area of the equatorial Pacific, known as the Nino 3.4 region, climb to or surpass 2 degrees Celsius above the long-term average. An anomaly of this size in this particular stretch of ocean represents a forcing event so powerful that it can trigger some of the most extreme weather responses ever recorded. It marks the difference between an El Niño that simply rearranges global weather patterns and one that fundamentally breaks them. The definitive benchmark for such an event remains the one from 1997 to 1998, which stands as the most intense on record by multiple measures. Its consequences offered a stark, worldwide demonstration of what a maximally forced El Niño response looks like, with catastrophic flooding inundating parts of South America and East Africa. At the same time, Australia and Southeast Asia endured severe, prolonged drought, which fueled some of the most devastating forest fires Indonesia had ever witnessed. North American weather was also significantly disrupted, with unusually warm winter temperatures across the northern United States that, while remarkable at the time, seem almost quaint from the perspective of 2026. A new Super El Niño is currently gathering strength in the equatorial Pacific, and it is not expected to reach its peak intensity until the period between November 2026 and January 2027. This leaves a window of approximately 6 months before the event's full power is unleashed. This 6-month gap is a crucial detail, especially when we consider everything else we know about the current state of the atmosphere. The amount of heat stored beneath the ocean surface in the equatorial Pacific, a vast reservoir of warm water that will eventually rise and heat the surface as the El Niño matures, is already at levels comparable to those that preceded the historic 1997-98 event. The warm water is already there, a silent accumulation of thermal energy moving deep beneath the waves. While it has not yet reached the surface in the volumes that will define the event's peak, the fundamental energy source that will drive that peak is already in place, waiting for the ocean dynamics that will bring it to the forefront in the coming months. This process is not happening in isolation. The atmosphere is responding in perfect, textbook synchrony. The critical feedback loop between the warming ocean surface and the corresponding wind patterns, known as atmospheric coupling, is developing right on schedule. This interaction further accelerates the warming. The trade winds, which are easterly currents that typically maintain the Pacific's normal state, are weakening in a manner that is a classic signature of El Niño development. Perhaps most telling is the fact that climate models from numerous independent institutions, each using different frameworks, are showing an unusually strong consensus about the eventual magnitude of this event. In the world of climate science, Such a high level of agreement among models this far in advance is itself a powerful signal that demands our serious attention. So, the stage is being set. We are witnessing a super El Nino developing along a trajectory that mirrors the most powerful event in our observational history, with its peak forcing still half a year away. Under any previous understanding of how El Nino seasons unfold, this set of circumstances alone would be more than enough to generate profound concern about what the coming winter might hold for North America. The historical record makes it clear that the teleconnection response to a peak super El Nino is anything but subtle, giving us a clear picture of its likely direction, even if its precise intensity remains uncertain. But here is the detail that should truly command our focus, the element that makes the current situation fundamentally different from any previous El Nino season on record. We are already observing 500 year-class heat events in the United States, and this is happening before the primary forcing mechanism has even truly engaged. The developing El Nino has not yet caused the substantial rise in global mean sea surface temperature that will occur at its peak. While the tropical Pacific is indeed warming, it has not yet triggered the full eastward shift in tropical storm activity that drives the most powerful teleconnection responses. The atmospheric circulation patterns over North America have yet to be significantly reorganized by the El Nino signal. The full force of the event is still months away, and yet, here we are. This brings us to a profound and unsettling question, a puzzle that has been called the timing problem. If the atmosphere is already capable of producing extreme events of this magnitude before the main driver has even arrived, what will it generate when that forcing finally reaches its zenith? If this is what the approach phase looks like in early May, before the El Nino has substantially reshaped atmospheric circulation, what will November look like? What can we expect in January of 2027? When the El Nino is near its peak and its teleconnection effects are at their strongest and most organized, a simple, linear projection of the current behavior produces an answer so alarming that even speaking it aloud feels incautious. But the atmosphere operates on its own terms, indifferent to what we find appropriate to say. Of course, a crucial and honest caveat must be stated clearly. The Earth's atmosphere is not a linear system. It does not behave like a simple, predictable machine. Extrapolating directly from current conditions to the behavior at peak forcing assumes a proportional relationship between cause and effect, which is not how complex systems work. These systems are defined by thresholds, nonlinearities, and feedback loops that can make simple projections unreliable at the extremes. The atmosphere's response to the peak El Nino will depend not only on the magnitude of the forcing itself, but also on the state of the entire system, the land surface, soil moisture, snowpack, and wildfire fuel conditions when that forcing arrives. And those conditions are being shaped right now by this very heat dome, by the fire weather it creates, and by the early snowmelt it is driving. The path to the peak runs directly through the events of today. When we strip away all assumptions and projections, we are left with one fact that can be stated with complete confidence. The baseline state of our atmosphere, the average background condition from which all extreme weather emerges, has already shifted. It has changed enough to produce 500 year-class events even before the arrival of the major, periodic forcing that we have been bracing for. This realization suggests that the very foundation from which we measure and anticipate extremes has been irrevocably altered. This single fact carries a specific and quantifiable consequence. It signifies that when the primary forcing event does manifest, any extreme weather will emerge from a baseline that is already higher than during any previously recorded El Nino. A super El Nino event occurring on top of our present, elevated atmospheric baseline is a fundamentally different phenomenon than one that occurred in the mid-20th century. The two are not even remotely comparable. This shift in the baseline does not merely add to the El Niño forcing in a simple, linear way. The interplay between a warmer, more energetic atmospheric state and a powerful El Niño is incredibly complex and not fully understood simply because we have never witnessed a super El Niño develop from a starting point this high. We are navigating territory for which our observational records have no direct map. The direction of the effect, however, is clear. A warmer baseline provides more available energy for extreme events, and more energy means these events will deviate further from the average. When a super El Niño interacts with this warmer baseline, it produces compound extremes that are far larger and more unusual than what either the warming or the El Niño could produce alone. The interaction is an amplifier, pushing the tail of the statistical distribution further out. Events once considered genuinely rare become less so, and what was once exceptionally rare becomes the new benchmark for rarity. The very language we use to describe these events must shift. This is what the next 18 months could represent, not just another El Niño season, but something different in its very nature. We are witnessing a forced experiment, where the climate system's most powerful periodic signal engages with an atmosphere already pushed beyond its historical range of normality. We are about to run an experiment with the global atmosphere that has no direct historical precedent, because the baseline has never been this elevated when a forcing of this magnitude has arrived. We are about to observe that experiment from the inside. The persistent heat dome, the ridge of high pressure marching eastward over the Rocky Mountains, the century-old temperature records being broken. None of this is the main event. All of it is merely the prologue. The critical fire weather building across the northern plains, even before the peak of summer, is just a sign of what is to come. The fundamental question is not whether we are prepared for what is coming. The more pressing question is whether we even possess the right framework to comprehend it when it finally arrives. Part 19. Conspiracies, misreads, and real unknowns. Every time a major extreme weather event occurs, particularly one that shatters records and captures widespread public attention, a parallel conversation begins to unfold. In certain corners of social media and online communities, a narrative takes shape that frames the event not as a product of understood atmospheric physics, but as the result of deliberate human intervention. These are theories of weather modification. Continent-scale cloud seeding programs run in secret, or electromagnetic manipulation of the jet stream. They speak of technologies capable of redirecting high-pressure ridges across mountains, parking them over specific regions to achieve specific outcomes. If you have spent time in online spaces adjacent to weather discussions, you have likely encountered these ideas. They tend to follow a recognizable pattern. An extreme event happens. Someone observes that it is unusual. Another person suggests it is suspiciously so. Then, a third party introduces a technology, whether real or imagined, that could theoretically cause some aspect of what has been observed. From that point, the conversation accelerates, drawing energy from the genuine uncertainty of extreme weather forecasting and the fact that most people, through no fault of their own, lack the scientific background to evaluate the claims being made. We are going to address these ideas directly because those who find these explanations compelling deserve a serious and honest response, not simple dismissal. Dismissal is easy, but it is also ineffective. It fails to engage with the underlying questions that make such conspiracy frameworks appealing, and it distracts from the things that are genuinely worth being alarmed about, which are often far more unsettling than anything the conspiracies propose. So, let us examine this properly. We can begin with the most frequently cited technology, cloud seeding. Cloud seeding is a real and operational weather modification technique, not a fringe theory. Its history dates back to the 1940s, when chemist Vincent Schaefer discovered that introducing dry ice into a supercooled cloud could trigger the formation of ice crystals and, ultimately, precipitation. The modern method is more refined but follows the same principle. It typically involves dispersing silver iodide particles into clouds that already contain supercooled liquid water, using either aircraft or ground-based generators. The silver iodide provides a surface for water droplets to freeze onto, acting as ice nuclei. This process promotes the growth of ice crystals that eventually become heavy enough to fall as precipitation. Under the right conditions, in the right types of clouds, cloud seeding can measurably increase rainfall from individual storm systems. It is crucial, however, to understand what cloud seeding does and, more importantly, what it does not do. The technology works by enhancing precipitation from clouds that already exist and already contain the necessary supercooled water. It cannot create clouds out of thin air. It does not generate moisture, nor does it produce the atmospheric instability required for storm systems to develop in the first place. Most critically for this discussion, cloud seeding operates at what meteorologists refer to as the mesoscale. This means it affects individual cloud systems or small clusters of them over areas typically measured in tens to a few hundreds of square miles. Even the largest operational cloud seeding programs in the world, which are run openly by governments and water authorities in places like China, the United Arab Emirates, and the Western United States, are designed with this limitation in mind. Their goal is to enhance rainfall from existing weather systems over specific watersheds or agricultural regions. At that scale, they can and do produce measurable results. The technology is real, but its capabilities are precisely defined and limited. The notion that human technology can steer weather on a continental scale often falters when confronted by a single, immovable obstacle: the physics of energy. These systems do not produce detectable effects at such a vast scale because the energy required to influence atmospheric features spanning a continent is incomprehensibly larger than anything our current technology can deliver. To make this comparison concrete, we must look at the numbers. A significant cloud seeding operation might disperse a few kilograms of silver iodide into a target area. In stark contrast, the energy budget of a continental high-pressure ridge, like the one we are observing, is measured in petajoules. A single petajoule is a quadrillion joules, or 10 to the 15th power. For perspective, the atomic bomb that detonated over Hiroshima released about 63 terajoules of energy, which is 6.3 times 10 to the 13th power joules. The energy sustaining the current heat dome is orders of magnitude greater than that, and it is maintained continuously, day after day, across millions of square miles. The idea that any human technology could create, maintain, or redirect such a colossal energy budget is not a question of secret capabilities or political will. It is a matter of fundamental physics, where the numbers simply do not add up. Claims of electromagnetic manipulation, which frequently point to facilities like the High-Frequency Active Auroral Research Program, known as HAARP, fail on similar grounds. These theories, however, are compounded by a misunderstanding of what these research installations actually do. HAARP, a facility in Alaska that has become the focus of numerous conspiracy theories, is a tool for ionospheric research, formerly operated by the Air Force and now by the University of Alaska. Its purpose is to transmit radio waves into the ionosphere, the highest layer of our atmosphere, located at altitudes above 80 kilometers. This allows scientists to study how this layer responds to radio frequency energy. But the ionosphere is not where our weather occurs. All weather phenomena take place in the troposphere, the lowest layer of the atmosphere, extending up to roughly 12 kilometers. There is no meaningful physical coupling between the ionosphere and the troposphere on the timescales or through the mechanisms that HAARP operates. The physics that would connect these ionospheric disturbances to surface weather patterns does not appear in any peer-reviewed literature, because the coupling mechanism itself does not exist at the required magnitude. To suggest that HAARP is steering a continental ridge across the Rocky Mountains is analogous to suggesting that turning on a flashlight in your attic could somehow guide your entire house across the street. The scales involved are simply incommensurable. So, why is it important to spend time clarifying this in a discussion of atmospheric science? The answer unfolds for two reasons, with the second holding even greater weight than the first. The first reason is a commitment to simple accuracy. The atmospheric dynamics propelling the current heat dome are largely understood. While our understanding is not perfect in every detail, the operational forecast models, for instance, did not perfectly capture the timing of the ridge's failure to follow its predicted life cycle. The broad physical framework is well established. The formation of the omega block, the role of Rossby waves in sustaining the pattern, the subsidence mechanism that generates compressional warming, and the overall energy budget are all documented and traceable in observational data. The event is certainly unusual, but being unusual is not the same as being mysterious. One implies a rare but natural occurrence, while the other suggests a hidden, unnatural cause. The second, more critical reason is that the conspiracy narrative, regardless of the intentions behind it, actively distracts from the issues that are genuinely worth our alarm. These real concerns are considerably more frightening than any weather control program because they do not come with an off switch. The true unknowns in this story are not the result of human agents carrying out secret agendas in hidden facilities. Instead, they are the genuine scientific uncertainties that sit at the very frontier of atmospheric research. These are the areas where our current tools, data, and theoretical frameworks are proving insufficient to answer the questions being raised by our atmosphere's present behavior. These are the questions that truly matter, and they point to a much deeper and more complex challenge. These profound questions are where the real mystery lies. Researchers are asking, are Rossby waves in the northern hemisphere's mid-latitudes slowing down in a way that makes blocking patterns, like the current ridge, more frequent and persistent? If so, is Arctic amplification the primary force behind this change? They are also investigating whether wildfire smoke creates feedback loops on atmospheric stability that are significant enough to measurably extend the lifespan of heat dome events. And if that is the case, are our forecast models systematically underestimating the persistence of these ridges in fire-prone regions? Another critical question is how a super El Nino interacts with an atmospheric baseline that has already been pushed far outside the range of historical variability. Does this compound forcing produce outcomes that are qualitatively different from what either force would create in isolation? These are hard problems, not because the scientists working on them are lacking in skill or motivation, but because the atmosphere itself is a nonlinear, coupled, multi-scale dynamical system. In this system, processes operating at vastly different scales interact in ways that are incredibly difficult to observe comprehensively and model completely. Our observational network, while remarkable, has gaps. The satellite record, though transformative, covers only a few decades at the resolution needed to study long-term changes in atmospheric dynamics. And our models, while impressively capable, are parameterized using assumptions about physical processes. These assumptions, tuned against historical climate data, may need significant revision as our climate shifts into uncharted territory. These uncertainties represent the true enigma of the current atmospheric event, and this is precisely why they are more alarming than any theory about human weather control. A conspiracy theory implies an agent, and an agent has motivations that can, in principle, be understood, constrained, or opposed. If a person or group were genuinely controlling the weather and causing harm, there would be a tangible target for action. The scientific reality, however, offers no such simplicity. It points not to a hidden villain with an off switch, but to profound, systemic changes in a planetary system we all depend upon. The absence of a simple agent to blame or a single lever to pull is perhaps the most sobering realization of all, forcing us to confront a far more complex and challenging truth. The genuine mysteries of atmospheric science do not conform to a simple narrative. They are not the result of any single decision, but are instead the emergent behavior of a physical system of extraordinary complexity. This system is now responding to pressures it has not encountered in the entire era of human civilization, and possibly not for the entire duration of our species' existence on this planet. It is a reality that offers no single agent to expose, no convenient off switch to flip. There is only the atmosphere, doing what physics requires it to do under the conditions we have created, and the urgent, underfunded work of scientists trying to understand it well enough to anticipate its next move. If there is a horror story hidden within current events, it is not that someone is controlling the weather, but that no one is. The atmosphere is operating on its own physical principles, responding to its own forcing, and producing consequences that our forecast models did not fully anticipate. Our infrastructure was not designed for this, and our frameworks for risk were not calibrated to handle it. And the people who understand this best, the atmospheric scientists, the NWS forecasters choosing their words so carefully, the attribution researchers running their analyses are working as hard as they can with the tools they have, trying to stay ahead of a system that is moving faster than anyone is entirely comfortable with. In a strange way, the idea of a conspiracy is more comforting than the truth. If a human agent were causing this, then a human agent could also stop it. The truth is far more challenging. What is happening in the American atmosphere right now is the product of physics. It is physics operating at a scale and in a regime that is new to us. This new reality is being documented in real time by instruments, satellites, and observational records that are all pointing in the same direction. It is happening in plain sight, measured by instruments anyone can access and captured by satellites whose data is publicly available. It is documented in forecast discussions posted on government websites by meteorologists who are not hiding anything, but are in fact trying desperately to communicate exactly what they are seeing. The mystery is not concealed. It is just genuinely difficult. And genuinely hard problems in a changing system with uncertain futures are somehow always less satisfying than a hidden villain. But the atmosphere does not care what satisfies us. It only cares about the physics. And right now, the physics is doing something that deserves our full, undistracted, clear-eyed attention. Let us return to where we began, because every piece of this story points toward the same fundamental truth. In early May of 2026, a ridge of high pressure formed over the American West. It was the first phase of what was expected to be a significant but manageable heat event, an omega block that models and forecasters understood. It was predicted to build, peak, and then collapse on a roughly 10 to 1 4-day life cycle that could be clearly communicated to the public. But that ridge did not follow the script. Instead of weakening, it amplified. Instead of dissipating, it consolidated. And then it began to move east, crossing the Rocky Mountains and establishing itself over the high plains. This single system threatened a Denver temperature record that has stood since 1915. It generated multi-day critical fire weather conditions across the northern plains, the kind that have produced some of the most catastrophic wildfires in recent American history. And at the same time, it loaded the atmosphere along its eastern edge with the instability and moisture that the Storm Prediction Center began to flag for potentially significant severe weather outbreaks. This is a cascade of consequences from one system breaking its expected life cycle. None of it is a coincidence. The record heat, the fire weather, and the potential for severe storms are all coupled. They are all products of the same amplified ridge. To see them as isolated events is to miss the story. The story is the ridge itself, and what it means that it behaved the way it did. The implications of this behavior are profound. It means that the atmospheric pattern we are living inside is capable of producing extreme outcomes across multiple risk categories simultaneously, all from a single system. This is no longer a vanishingly rare statistical extreme, but something that is now happening with a frequency that challenges the very statistical frameworks we use to define rare events. It also means that a pattern we thought we understood, the heat dome life cycle, with its expected arc of building, peaking, and decaying, is not as reliable a predictive framework as we once assumed. When a system consistently breaks its expected life cycle, not as a one-time exception but as a pattern of behavior, the implication is that the framework itself needs to be revised. The atmosphere is not broken. It is operating by its own physics, faithfully and precisely. What is being revealed is that our models of those physics, calibrated on a historical atmosphere that no longer fully represents current conditions, are carrying systematic biases. These biases cause them to underestimate the persistence and amplification in these heat dome events. This tells us that the 2500 year-class events that have already occurred in 2026 are not a streak of bad luck that the law of averages will eventually smooth out. They are data points in a distribution that has fundamentally shifted. The expected recurrence interval for events of this magnitude is shorter now than the historical record would suggest, because the atmospheric baseline has moved toward conditions that favor their production. What was a 500-year event in the mid-20th century climate is something more frequent now, and it is becoming more frequent over time. And finally, it means that all of this is happening before the super El Nino developing in the equatorial Pacific has even reached its peak. We are watching the preloading phase. The atmosphere is accumulating energy, building patterns, and producing extreme events at a rate that, in the historical record, would be associated with peak forcing. Yet the peak is still 6 months away. The question of what happens when that peak forcing arrives in an atmosphere that is already behaving this way is one that the climate scientists who understand it best are genuinely uncertain about. And in this case, their uncertainty is not reassuring. When faced with events that fall genuinely outside the scope of direct historical experience, we are forced to reconsider our assumptions. This leads to a central question that weaves through every other observation, a question for which no current dataset or forecast model holds the answer. Are we simply watching a series of unusual events, a bad season, a cluster of extremes that will eventually pass, or is this a true transition? Could we be seeing a fundamental shift in the character of the American atmosphere? This would mean a new regime is taking hold, one that alters the very baseline from which weather departs and increases the frequency of extreme events at the most dangerous end of the spectrum. A climate undergoing a regime transition does not announce itself with one singular event. It is a gradual change in statistical behavior, becoming visible only after enough data has been gathered over time to confirm that the entire distribution has shifted. The unsettling possibility is that we are living inside such a transition right now. The atmospheric ridge that defied expectations and refused to collapse may not be a mere anomaly. It could be an early and well-documented example of an emerging new normal. In this new paradigm, ridges would amplify for longer periods, persist with greater stubbornness, and migrate more forcefully across the continent. This would produce compound extreme consequences with a frequency that nothing in the historical record would have led us to anticipate. If this is true, then the next 18 months will not be a temporary deviation from a stable known pattern. They will represent the period in which the new statistical behavior of the American atmosphere becomes undeniable to any honest observer. The anticipated super El Nino will arrive, and this new atmospheric baseline will be there to meet it. The resulting compound extremes will impact infrastructure designed for a different atmosphere entirely. They will challenge institutions calibrated to a different baseline, and be evaluated by risk frameworks that rely on an increasingly irrelevant historical record. A ridge that was supposed to dissipate instead marched east across the Rocky Mountains, proceeding to break records that have stood for 111 years. This is the single data point that began our inquiry. Everything else we have examined, the fire weather, the severe storms, the timing of ENSO, the statistical clustering of 500-year events, the speculative feedbacks, and the historical parallels that no longer seem to apply, is downstream of that one anomalous behavior. It was a system that broke its expected life cycle. What the atmosphere does next will tell us a great deal about whether that broken life cycle was simply an exception or a preview of what's to come. The forecasters are watching, the models are running, the ridge is moving, and what happens over the next 18 months may not just define a weather season. It may, in fact, define the kind of atmosphere our children will inherit.